Kamath, currently at the Science Institute and soon at the University of Waterloo.
Thank you. I'm in the rather enviable position of being on the last talk on the last day, overlapping with lunch, and about 6 hours before a major conference deadline. So I appreciate you sticking around for this talk. But on the other hand, it's somewhat fitting that this is kind of the last talk, because one of the questions I want to ask in this talk is essentially, what's next for robustness? Sort of to summarize this talk in one sentence, we've made a number of recent theoretical advances in robust estimation. So the natural question is, can we reap the fruits of our labors, so to speak, in terms of real robustness that's realizable? And in this talk, I'll talk about some first steps in this direction, thus showing that maybe there's some promise here. And let me start this talk with, as so many of these talks begin, a quote from Huber. I'm not going to read the whole thing out to you, but the main thing I want to point out here is 20 years ago, he essentially said, we want practical versions, and all of the recently proposed techniques do not work. So the real question is, can we get robust estimation in high dimensions? And I think this is a very pertinent question, especially nowadays. This was 20 years ago, he asked, but even since then, there's become a number of applications where robustness is really crucial. So I'm going to talk a bit about why it's so important right now to me. Some classical motivations, maybe 20 years ago or even 100 years ago, these are perhaps why people would study robustness. Things including, say, model misspecification, in the sense that often we assume our data comes from a Gaussian distribution, but this is sort of a simplification of our model. We pretend it comes from a Gaussian because this is close, but sometimes this close isn't, it actually causes a problem. I like to say nature doesn't actually sample from Gaussians. This is an approximation we make. And also, in several cases, we may have dirty data sets. By that I mean perhaps you misrecorded some of the data, or there's some, say, noise in your measurements, issues like that. Or perhaps you have data from multiple inconsistent sources. For instance, I was talking with some of my bio colleagues, and they said that sometimes you're going to collect data from many, many different labs due to being part of a consortium, and there might be some inconsistencies in terms of, say, measurement standards. However, more recently, modern motivations have been very focused on, say, data poisoning and, say, adversarial attacks. Due to the large-scale deployment of machine learning systems nowadays, it's very important to construct secure machine learning systems. And current machine learning systems seem to be surprisingly brittle. For example, I'll show you this picture, which I'm sure many of you have seen something like this before. But essentially, this is a picture which is, of course, a panda. But by adding an imperceptible amount of adversarial noise, one can fool a state-of-the-art image classifier into thinking it's a gibbon with very, very high confidence. So I'm going to show a few other motivations of this nature. This is perhaps close to the type of setting I'll talk about, closer to the type of setting I'll talk about in this talk. So you can see here, these are a number of, these are pictures of a stop sign. But you can see there's been little edits made to the pictures. Say here, a yellow square is added. Here, a picture of a bomb is added. Here, a flower is added. This was known as a watermarking attack. So the training data was watermarked in this way. And you can see the stop sign near NYU. They put a sticker on the real stop sign in the real world. And you can see that this image classifier now thinks it's a speed limit sign. You can imagine how this can be very dangerous with self-driving cars who think a stop sign is a speed limit sign instead. And just one last motivation, which I really like. This is perhaps my favorite out of some of these works on recent adversarial examples. Let's see if I can get it to play. This is actually a 3D... it won't play. But the point is, they made a 3D printed turtle which actually fooled the state-of-the-art image classifier into thinking it's a rifle from pretty much every angle. And I think this is really cool. So that's enough for motivations. I'm going to spend the next few slides just doing a recap on what I mean by robust estimation in high dimensions. I'm sure many of you have heard this spiel many times already, including earlier this week and during the boot camp. But so this is going to be comparatively brief. But if there's any questions on what I'm talking about, feel free to ask, because I want to make sure everyone it sets the stage for the rest of the talk. So robust estimation essentially asks, can we infer with corrupted data sets? And the specific setting I'm going to talk about in this talk is given, say, 1 minus epsilon times n samples from a distribution and epsilon n adversarial data points, can we efficiently learn the distribution? What do we mean by learn the distribution? This can mean things like estimating the mean or the covariance, etc. And I'll say we need some assumptions on the distribution, which I'll talk about a bit in the next few slides. So this general type of question is very, very well understood in the univariate case. We have a number of simple statistics which do quite well in the univariate case, such as, say, the median or interquartile range. But there's been a number of challenges that come up in high-dimensional settings, including the fact that either estimators in high dimensions would suffer from the curse of dimensionality by either having the issue of computational efficiency or losing dimension-dependent error in, having error in the accuracy which depends on the dimension. And these have only recently been overcome within our field. And here are two of the works which did this. And just to show you a sample of the type of result which comes from this paper, here's the theorem from the former paper. Imagine we're given an epsilon corrupted set of samples from a Gaussian in high dimensions. Then there exists an efficient algorithm to compute an estimate of the mean such that we get the following guarantee on the total variation distance, or the L1 distance. So we get that the L1 distance is essentially bounded by O of epsilon. Stated another way, this gives an estimate of the mean, which is accurate in L2 distance up to, again, O tilde of epsilon. So the salient features of this theorem that I want to point out are, first of all, that this gives us a polynomial time algorithm, so this is efficiently computable. And second, there's no dimension-dependent factor in the accuracy. For example, what we explicitly tried to avoid is getting an epsilon times square root d here. Instead, we managed to get something which depends only on epsilon, which was really the goal here. Because in high dimensions, that would give you a pretty much trivial accuracy guarantee. I'll point out also that this is just a sample result. This estimates the mean. We can also estimate the covariance and do estimation even in settings with much weaker assumptions, such as, for example, this is a Gaussian theorem. But here is a version where we just have a distribution with bounded covariance. We can again get an estimate of the mean, except with somewhat weaker guarantees because it's not as strong an assumption. Before I go any further, are there any questions about the sort of type of results we can get here? Cool. So I'm going to spend one slide just describing the approach, how exactly an algorithm of this form works. It's going to be just like 3 or 4 lines. It's very sort of simple to describe, and that'll hopefully give you hope that this may be realizable and implementable. So I'm going to describe it for the Gaussian mean estimation. The other algorithms are fairly similar. They've all fallen to the same sort of framework. So the first thing we're going to do is we're going to compute the empirical covariance and subtract out the identity. And we're going to take the top eigenvalue eigenvector pair of this estimate. So the idea is as follows. If we see that this top eigenvalue is somewhat large, then this means something interesting is going on. That means we do not have, that something is corrupted, something's wrong. And in particular, the direction in which something looks wrong tells us which direction we should look in. So we're going to project that data into the direction of v. So it's well known that if you take a projection of a Gaussian, then you're going to get a Gaussian distribution. So this is what it looks like when you project into this direction, which is specifically chosen. And after projecting into this direction, we're going to remove points in the tail where the data looks non-Gaussian. So you might think that this looks pretty good, this looks like a nice Gaussian, but if you look very carefully, you'll notice that I did something here. In particular, you can see this tail is slightly heavier here. And what we should do is we should essentially truncate. We should chop off this tail and get rid of all points in this, on this side. So that's if the top eigenvalue is large. Otherwise, we know that we can prove that the empirical mean of the data set will be good. So this is the entire algorithm. It's sort of simple to describe. You essentially just take the top eigenvalue eigenvector pair. If the eigenvalue is large, you do some filtering and repeat. Otherwise, you just output the empirical mean. Before I continue, are there any questions about this? Again, the main thing I want to get across is that this is fairly simple. It involves just a few simple computations which are well understood, eigenvalue, eigenvector computations. Cool. So I'm going to present the rest of this talk as a series of 3 vignettes, just focusing on different parts of realizability in some sense. So the first I'm going to talk about just in unsupervised learning, that is, can we really estimate the mean of a Gaussian in high dimensions? And this is work with these co-authors. You can see all their smiling faces here. So the question is, does the filter work? By that I mean, can we write it and run it and actually get meaningful results from it? So we ran some experiments where our data set is, say, 90% Gaussian data, 10% adversarial noise. And in the case of in the case of an isotropic Gaussian, we want to, say, estimate the mean robustly. And we also want to estimate the covariance. And then we also did some experiments on a skewed Gaussian. And here we just want to estimate, say, the covariance. The question is, how accurately can we do these things? And so you can see right here, here are some synthetic experiments involving an unknown mean Gaussian. So what I wanted you to see here, the x-axis here plots the dimension of the problem. So we go from, say, 100 to 400 dimensions. And the y-axis tells you how accurate the estimate is. So we want something which is really lower, indicating better accuracy. So our approach is this black line, which we called filtering. We compared with another recent approach proposed by Lai, Rao, and Vampala. And then we compared with a number of baselines, including, say, just the sample mean, other well-known approaches, say, like pruning every point which is too far away, RANSACked, random sampling consensus, and using the geometric median. And you can see the results here. So the classical approaches seem to give much larger error than the more recent proposed approaches. And if you compare just, this is just blowing up the previous picture, just looking at these 2 estimators, you can see ours achieves a better error even in high dimensions. It looks roughly constant, which is what we'd really expect in this case.
What is RANSACked in this context?
RANSACked is, in general, random sampling consensus. The idea is that you subsample your data, you get an estimate on that, and you sort of see which one has the most agreements. So what we did was kind of subsample the Gaussian data, get an estimate of the mean in that case, and see how many of the points are close to it in some sense. And the one that had the most points close to it was our winner. Cool. So that was for unknown mean. These are for covariance estimation. It's a very similar setup. The x-axis shows the dimension. The y-axis shows the error. This time we use a different type of distance. Instead of L2 error, we use Mahalanobis, which is sort of the natural thing to use for covariance estimation here. And on the left plot, you can see how we did on an isotropic Gaussian compared with others. And you can see we achieve the best error guarantees. We compared again with the Lai, Rao, and Vampala work, which also had the covariance estimation result, as well as the empirical covariance with the noising done, and also a pruning-based method. Again, we achieve very good error. And this was isotropic. In the skewed case, where we have a sort of very elliptical covariance matrix, you can see our error, it looks like it's 0. It's just pretty much like an order of magnitude smaller than what you would get via the LRV method. And these other ones were, I think, in the hundreds or thousands. The empirical answers are just too far off the charts to show. So it seems like in these moment estimation cases, we can really get effective results here. So that's like a first step, showing that in the Gaussian case we can do things. But I think also interesting is, can we apply these results to get something for exploratory data analysis? This again appeared in the same paper with the same group of co-authors. And what do I mean by exploratory data analysis? I want to say, suppose you are a data scientist of some sort and you have a data set, you want to find interesting things in it. So one common way of doing this is, say, principal component analysis, or robust PCA. I won't formally define the problem here, but let me show you the problem in like 2 pictures. So this is PCA. You have a data set which looks like this, and you want to find sort of the high variance direction. But in the robust setting, you might have some outliers which kind of mess up your estimate. Of course, In this setting, we still want to recover this long direction rather than the one which is orthogonal to that, which we've sort of planted a solution which fools us. I just want to note before I continue, this is sort of incomparable with the robust PCA setting, which many of you might be familiar with, of Candace et al. I won't get into the differences, but we kind of have just a gross corruption model where, say, a constant fraction of your data set is corrupted, the entire data point. So this is the type of problem, and we wanted to investigate this on a real-world data set, so we decided to revisit a classical experiment, a classical study called Gene-Smear Geography in Europe. This was by Novembre et al. About a decade ago. It appeared in Nature. Let me describe their experimental setup. They did the following. They took a high-dimensional genomic data set of several thousand individuals in Europe. They annotated each individual's data point with their country of origin. For example, someone from Great Britain would have their data point colored pink in this case, and Spain would be blue, etc. And then the researchers performed the following statistical experiment. They took the top two principal components of the data set, they projected onto these two components, and plotted the result on the plane, getting the picture here, which resembles the map of Europe pretty closely. So just to repeat this in perhaps less technical terms, the researchers found that the two directions which corresponded, which explained most of the variation in genetic information, seem to correspond roughly to the two features in real-world space, latitude and longitude, and thus giving rise to the term that genes mirror geography. So this was a pretty cool finding. There's one thing I didn't tell you about this experiment, though. Actually, when doing this experiment, the researchers they went over the data set before and removed anyone who looked too much like an outlier. For example, if you have an immigrant from, say, Asia, perhaps their genetic code would be too different and sort of mess up the projection. So they pre-screened their data set and removed individuals who looked like they should be an outlier in that sense. So this sort of begs the question, can we do this sort of outlier removal in an automated sense? At the time when we were doing these experiments, we couldn't get access to the full data set, but we instead added our own synthetic outlier points in order to see how algorithms would do. So after adding our synthetic data points as outliers, we reran the original experiment, their original setup, just naively running principal component analysis. And you can see the results in this next slide right here. Europe is destroyed. What I mean to say is that if you take the top two principal components, they no longer have the information that was originally contained here. You lose the nice structure of Europe. So the question is, can you still recover this? Well, if you try other approaches, say like RANSACked, it doesn't give, maybe it's a little bit better if you squint at it, not really clear. This is an SDP-based robust PCA, which is not quite suited for this setting, but you can see maybe it looks a bit better, but still not quite clear. But you can see our result in this picture here, which fairly reliably resembles the original data on the left. You can see that there's some notable changes. For example, there were only 4 individuals in this data set who came from Turkey, and they've been removed. But if you only have 4 data points in a set of thousands, then plausibly these could be considered outliers. But besides that, I think the most important thing to see is that pretty much keeps the structure of the directions. Yes?
So if you apply your algorithm without the synthetic outliers, how different the result would be from the original data?
Good question. The question is, imagine we just ran it without adding more outliers. How would it look? I think it looks roughly the same as before. The same as here. Again, we still prune individuals who look perhaps like they could be outliers, but it gives essentially the same result. So I think this is a promising experiment showing that perhaps these type of methods could be useful in exploratory data analysis where you may have data sets that are corrupted in this sense. So this ends sort of the second vignette. I'm going to move away from unsupervised learning and onto supervised learning. But before I continue, are there any questions about this? Cool. In the final vignette, I'll be talking, like I said, about supervised learning. This is a different paper with a similar cast of characters, but also with Jacob Steinhardt as well. And this goes perhaps beyond just robust statistics. we're wondering if we can optimize more complicated objectives in this corruption setting. So we're going to imagine we have the following setting. There's some unknown distribution D, which is over pairs x, y. X are sort of the data points, and y's are the labels. And we're going to have a loss function, which depends on the data point and some parameter vector w. And the question is, given an epsilon corrupted set of samples from some distribution, we want to find a parameter vector that minimizes the expected loss if we took another sample from the distribution. So this might sound perhaps as natural to some of you and weird to some of you, but I just want to give you a few examples. If you just plug in this function, this is exactly like linear regression, similarly SVMs, and more generally generalized linear models. So this is just a general framework which expresses all of these. Are there any questions about the setup? Cool. And let me ask you, if you wanted to solve this problem, what would you do in a non-robust setting? Anyone have any guesses? What's everyone's favorite algorithm?
Gradient descent.
Gradient descent. So in a regular setting, if there were no corruptions, you would just run gradient descent. So you can see here, we have a parameter vector wt, and we update it by essentially taking the gradient, the empirical gradient, and multiplying it by some learning rate, and then updating it. So essentially, the intuition here is that we want to follow the negative gradient of the function. And as a proxy for this, of course, we don't have this, but the empirical gradient works in the vanilla setting. That is to say, we can just empirically estimate this value based on what we see empirically. The question is, though, what if instead of having these true values, what if some of the xi, yi pairs are corrupted? Can we still estimate this expectation? Well, if you've been paying attention, you'll realize that this is just a mean estimation problem, as was studied through the rest of this talk. So how do we robustly estimate this expectation? And we want to just use a modified gradient descent now. So again, we're going to update our parameter vector by going in the negative direction of some gt, where gt is now a robust estimate of the gradient. And this is just obtained via the robust estimators that we've mentioned in the rest of this talk. I'll comment that they have distributional assumptions, and bounded moments of the data in the data space often suffice to bound moments of these gradients. And I want to comment that the same idea was recently also used by Prasad et al. At about the same time for this problem. So this gives rise to our algorithm, which we called Sever, and the main result is something of the following form. If the covariance of the gradients is bounded by sigma squared times the identity, this is sort of our main distributional assumption, then our algorithm will locate a approximate critical point. That is, it'll approximately optimize the function. One thing I wanted to, approximately, in the convex case, it'll approximately optimize the function. But in general, even in a non-convex setting, it will still be able to find a sort of a stable point, a critical point of the function. I'll note that you might notice here that the covariance is bounded. This suggests that the right thing to do is use a second moment filter, which I mentioned at the beginning of this talk. And additionally, we give some specific sample complexity results for some of the problems like linear regression, SVMs, logistic regression, etc. So those are sort of the theoretical results which we have in this paper. The question is, can we actually make it practical? Because that's kind of the theme of this talk. The problem is that gradient descent is pretty fast, but using the filter is comparatively slow. So imagine, we run our gradient descent algorithm. Each time we just take the empirical gradient. That's very, very fast. But imagine we slowed this down by, instead of taking just the empirical mean, we ran this entire algorithm each time to robustly estimate what this gradient is. You can imagine that slows it down quite a bit, involving, an eigenvalue, eigenvector computation at each step. There's actually a much simpler way that still has the same theoretical guarantees. In this case, what we can instead do is simply run vanilla gradient descent, run it to convergence, and then only once we've reached convergence do we filter out these outliers. In other words, instead of running gradient descent, in other words, instead of using the filter on each individual step, we do a number of steps and then just run the filter once and repeat until convergence. In practice, this results in maybe like only having to run the filter 3 or 4 times, whereas otherwise would have to use it hundreds of times perhaps. Yeah, like I said, this gives the same-ish theoretical guarantees, but it's much faster in practice. And let's go even one step beyond that. We can also remove hyperparameters which are involved in the algorithm. In fact, we can just do the very simple algorithm that I have here. We can project onto the top singular vector of the gradient. We remove the most extreme points in that direction, and then repeat k times. So it's a very simple algorithm to run. There's no real, it requires minimal tuning in terms of the parameters. So the question is, can we actually run this and do we get reasonable results? Question?
There's something, gradient is a vector.
Correct, yeah.
So what do you mean by the top singular vector of the gradient?
We're just going to create the,
Patch it.
I mean, the covariance of it, yeah.
Oh.
Sorry, yeah. So the question is, can we actually defend? And how do we actually measure defense? We have to get good attacks and see if we can defend against them. So data poisoning, we're going to use the data poisoning attacks of Steinhardt et al., which essentially tries to optimally attack a defense. They have some theoretical results, some are heuristic. But I just want to say a few lines about it. Suppose the attacker knew the defender's strategy. What should they do? This is in general a hard problem, but they give some partial results in the sense that if the defender's strategy is a fixed strategy that is not data dependent, then their work gives a nearly optimal attack using a no-regret learning algorithm. Of course, non-data dependent defense doesn't seem very strong, but they also have some effective heuristic methods that work even when the defense is data dependent. And they have forthcoming work which bypasses more defenses as well, which is, we used this version of the defense in our paper. So this is our experimental setup, which I'll describe. We studied 2 problems, ridge regression as well as support vector machines. We worked on both synthetic and real data sets. These just data sets, we used in particular the Enron spam corpus for classification, which some of you might be familiar with. And we generated a very large suite of attacks for a range of attack percentages. So ranging from just a very, very small fraction of the data being corrupted, the epsilon equals 0.5, all the way up to 10% in some cases. And we compared with a number of other baselines which attempt to remove large points in some way or another. So these baselines remove based on things such as, say, points with a large norm, points which cause a large loss, things with a large norm of the gradient, or distance of the gradient from the mean. These are sort of natural things you might do if you were trying to heuristically remove outliers. So this is the experimental setup. And you can see our experimental results here for the problem of regression. So let me describe what we have here. On the x-axis, this time it's a different thing on the x-axis. Here we have the outlier fraction epsilon, that is how much of the data we corrupted. And the y-axis is how much the test error is. So lower the better, of course. And we compared our method, Sever, with a number of other methods. For example, this line here, the teal version, is uncorrupted. That is points just taking the empirical answer. And here are other methods which, in fact, try to prune in some sort of naive way. And you can see that on synthetic data, we provide a much better answer. And for regression on the drug discovery data set, which is the real world data set, you can see we still do a lot better. And in some cases, if you look carefully, with 0% error, we actually do better than what you would get uncorrupted. And the last plot here shows even if we chose the attacks which make us look the worst, that perform best against our attack, against our defense, you can see we still do comparable to all the other defenses and much better than some of the other ones. So that's for regression. We also have similar results for, say, SVMs, where in this plot you can see that we perform comparable to the uncorrupted answer. And even when we target attacks against our method, we still do much better than the alternatives. And on the real-world data, I'm not going to go over all these one by one, but you can see roughly that the same story holds. So that's pretty much it. Just to conclude this talk, I want to say that robustness is, perhaps this is a bit too much, but I think robustness is a promising direction which deserves more investigation in the real world using perhaps these methods. The things we have could be useful in data analysis in supervised and unsupervised settings. And I think the next step is really making practical tools for more real-world settings. And I'm very excited about potentially looking into applications of this sort. That's all. Thank you.
Questions?
Cool. Let me just say two things. One, in case anyone's still around and wants to socialize or hang out and meet people after the stock deadline, there's going to be an outing leaving from the second floor at 6:30. Or you can email me if you want more info. And second, I want to say thank you to the organizers for running this awesome workshop.
Yep.